So currently we want to do, we want to find all the primes in this range. Then we know to determine if a given number somewhere, so anywhere in this range, if it is a prime, remember we need to check all the possibilities, right? Remember, so last time we exhaust all the possibilities for the AB pairs last time. So it's relatively hard to determine if a given positive number is a prime or not. But it is relatively easier to determine if a given positive number is a composite number. Okay? Yeah. So, yeah, because here, this idea in problem solving also quite common. Yeah, people use the idea. So, when we working on the data, so I draw the circle to represent all the data we need to process. But in the data, in this circle, all the data can be divided into two different categories. All right. So here, one category is a prime category. Second, composite number category. Okay, all right. And these two types of numbers, they are complementary each other, right? Complementary each other. Yeah. So in this situation, when we work on the prime numbers relatively hard, then an easier way is we can work on its complementary part, the composite number part, because that part is easier. Yeah. So we want to solve this problem using some easier way. Yeah. So based on this idea, now we want to work on the composite numbers. Determine all the composite numbers. Then we cross out. Okay? So if there's a composite number in the list, let's cross it out from the list. Yeah. If the idea is like this, the strategy, so here, our problem solving strategy here, if we can cross out all the composite numbers in this range, then the remaining numbers are the prime numbers. Okay? Yeah. That's simple strategy, yeah, to solve this problem. All right. So let us implement the strategy. Yeah. Remove all the composite numbers. Yeah. Okay? Yeah. Then the prime numbers remain. Yeah. That's simple strategy. Okay? All right? So let's implement. The next question, how to remove all the composite numbers? Okay. Yeah. How to use some easier way to remove composite numbers. Yeah. So that's this ancient very old, approximately in 3rd century. Yeah. 3rd century. Yeah. The reference, the earliest reference of this algorithm in 3rd century. Yeah. So sieve of Eratosthenes algorithm. Yeah. All right. Then, now we need to work on the details. How to list all the composite numbers in this range using some simple way. Yeah. Simple way. Okay? All right. Yeah. If we recall, the basic operation we studied before, n equals a times b. Yeah. When we have n, then we try to figure out which AB pair can we find such that A times B equals N? That way, that's the decomposition way, right? So we do decomposition. So N is known, okay? A, B unknown. A, B unknown, okay, yeah. From known to unknown, so it's a decomposition process. And here, this decomposition process relatively hard. Why? A is unknown, B is unknown. Yeah. So A, B unknown. Yeah. How do you get A? You need to make a guess. You need to guess that A and do testing. Yeah. You need to make many guesses. Guess A values many times. Every time when you have a guess, you need to do testing. Okay? So that process relatively time consuming, right? Yeah. Relatively time consuming. Yeah. All right. Yeah. So here, yeah, because yeah, I need to. Yeah. So let me see. This student. This student. Oh, why I can? Yeah. Because if I click this button, my PowerPoint slides may be disabled. Yeah. Yeah. Let me try. If it's disabled, yeah, good. Yeah. This time it works. Yeah. Because before, when I do that, when I do some action, then my remote control is disabled. Yeah. All right. Yeah. We can continue. Yeah. All right. Yeah, decomposition process relatively hard. Okay, yeah. So here you can see, when we solve some problem, we try to find some easier way to solve. Yeah. All right. So here the strategy. Yeah, yeah. Remove all the composite numbers, but the question how to. Yeah. So we want to find a relatively easier way how to determine the composite numbers. Yeah. And decomposition way is relatively hard. Yeah. So we don't want to go that decomposition way. We want to go the opposite way. The opposite way of the decomposition. What's that? Decomposition. Okay? Yeah. The backward. Yeah. The reverse of the decomposition. So that's the multiple way, right? Multiple way, that's the opposite way of decomposition. Yeah. So here we take the view, we take the multiple view. Remember that in our last lecture, I talked about the multiple view. Yeah. So N we treat it as A multiple of B or B multiple of A. Remember that view. Yeah. Here we want to take that view. Multiple view. Use the multiple view to replace the decomposition view, because that will be much easier. If we take the multiple view, we can reduce the number of testing. Yeah, because when you make a guess of A's, you need to do a lot of testing, right? Yeah, but when we use this multiple view, we can avoid testing. Yeah, so that's the nice thing. Yeah, yeah, because for each composite number, we only need to do one multiple try. One multiple try, we can determine one composite number. One try, okay? One test. Yeah. In other words, we can call it one test. We can determine one composite number. Not many tests. If you use the decomposition process, you need to do many tests, not just one. So, because when you make a guess, many times your guesses may not be correct. Yeah. But if we take the multiple view, one try, we can get a one composite number, right? Yeah. So that way it's much easier. That view, that direction, much easier. Yeah. So now let's do that easier, faster, easier way to find out all the composite numbers here. All right. The critical view, the composite number first. Yeah, because here, now we are looking at all the multiples, okay? All the multiples, yeah, so here, yeah. Let me write it again. Yeah, n equals AB, right, yeah. So all the possible multiples, yeah. But when we, so think about all the possible multiples generated from AB numbers in this given range. Yeah, that's our data. So currently we study the data. So what is the data we are interested at this point? Yeah. All the AB pairs, yeah, but AB, these two numbers come from the given range here. Okay, all right. Look at all the pairs. That's our data. But when you want to find all the multiples, or I call it a non-trivial multiples. Non-trivial. But trivial multiple, we're not interested. Trivial. 1 times n, okay? 1 times n, that's the trivial multiple. So we don't want to look at the trivial multiple. We want to look at the non-trivial multiples. Yeah, AB in the range. Yeah, but because 1 is out of the range, right? And also out of the range. Yeah. But anyway, you know, the two factors in the multiple, none of the two factors in the multiple can be 1. Okay? If one of the two factors is 1, so we call it trivial multiple. Okay? It's not non-trivial multiple. Yeah. All right. So next question. How to find out all the non-trivial multiples from the given range? Yeah. Then we need to use the idea we learned from our first problem, the chessboard problem. Remember the chessboard problem? We need to organize our data. Yeah. Here, because all the pairs very messy, right? All the pairs in this range very messy. Yeah. So we want to organize our data, characterize our data. Okay? Characterize our data. Yeah. So then the first category, we need to divide our data into many categories. So the first category is multiple of 2's. Multiple of 2's. Okay? Or precisely non-trivial multiples of 2's. How about that? Trivial, 1 times 2. Yeah. So we don't want to count 1 times 2. That's the trivial multiple. Okay? So the non-trivial multiples of 2's. Yeah. All right. That's the first category. Okay? All right. Second category, non-trivial multiples of 3's. Then, and so on. Okay? Next. Yeah. Yeah. And but what's the next one? Next one, if you want to call non-trivial multiples of 4, because when you consider multiples of 2's, the first category already contains the multiples of 4, right? Yeah. Yeah. So after that, we should consider multiples of 5. Yeah. Yeah. So you can see this number should be a prime number. Should be a prime number. 5, then 7. Things like that. Okay? All right. Yeah. All right. So that's the idea. Yeah. Now, let me use this example. Yeah. So let me consider the integers in the range from 2 through 100. the largest 100. Now we apply this sieve idea. Yeah, that's the sieve idea. Okay? The sieve idea, we go through our data set, multiple rounds. For each category, we process one round. Yeah. The first round, we cross out all the non-trivial multiples of 2's in this table. Okay? Yeah. All right. So cross out all these numbers. Yeah. But not 2, because that's the trivial multiple. So we keep it. Yeah. We keep it. Yeah. Actually, it's a prime. So we don't want to cross out a prime. Okay? Yeah. Yeah. So the first round, cross out non-trivial multiples of 2's. Second round, we cross out non-trivial multiples of 3's. Yeah. So look at 3's. I use different color. Cross out. Okay. Yeah. So yeah. If we already some numbers, they are both the multiple of 2's and the multiple of 3's. If the first one we already cross out, then it's gone. So the second time, we do not need to do anything because they are already gone. Okay? Yeah. So we only cross out the, those numbers that remain after the first round. Yeah. All right. So next round, multiple of 5. Non-trivial multiples of 5. Okay? Yeah. Cross out. Okay. All right. The sieve. That's the sieve. Yeah. Sieve. Round by round. Yeah. Then the fourth round, non-trivial multiples of 7. Yeah. Another color. Yeah. All right. 7. So 4 rounds. First round, non-trivial multiples of 2. Second, non-trivial multiples of 3. Third, non-trivial multiple of 5. Fourth, non-trivial multiple of 7. Then the question. Next question. Should we do another round sieve? Yeah. So the number in our table still there. Yeah. The next one. Yeah. Oh, yeah. Because after 7, 11 is the next one. Yeah. The question, should we cross out the non-trivial multiples of 11 in the table? That question. Yeah. Yeah. Although, based on our original algorithm design, we should do that. Yeah. But actually, we do not need to do that. We can stop. After 7, we can stop. Because it's enough. The remaining numbers are all prime numbers. Yeah. The remaining numbers are all prime numbers because you cannot find composite numbers in the remaining part of the table. You cannot. Okay? Yeah? So why? Why is that? Yeah? Why is that? Why we only need to do 4 rounds? Then it is guaranteed that all the remaining numbers are prime numbers. Yeah. That's another important property. That property in our understanding phase, we didn't discover it. Remember, at that time I asked you, what property can we discover? At that time, we couldn't see any special property. Yeah. But here, after we work on the data, the specific example, now we can see there is some interesting property here. This property, why we can stop after 7. Yeah. All right, so let me explain that property. Yeah. That property. Yeah. All right. How do you know it is correct? Yeah. How do you know after you stop, after the fourth round, you get all the prime numbers? That conclusion is correct. Okay? Yeah. We need to prove it. Yeah. We need to prove it. Yeah. All right. So here. Yeah. Another question. Why it is enough to only do eliminations for the composite numbers in 4 rounds? Yeah. You don't need to do another round. 5th round. No need. Yeah. If you do the 5th round, you get nothing. Yeah. You cannot cross out any non-trivial multiple of 11. Okay? Because all the non-trivial multiples of 11 already cross out in the first 4 rounds. In the first 4 rounds, you already cross out all those multiples. Yeah. So you don't need to do anything. Yeah. So here I need to show you. Yeah. This property. Yeah. We need to use this, interesting property here. Yeah. All right. Let's look at this decomposition form. N equals A times B. Yeah. Let us consider the range for A. Yeah. A is a smaller factor in the AB decomposition. In AB decomposition, we have 2 factors, A factor and a B factor, and we assume A factor is a smaller factor, B factor is a larger factor, but they could be the same. Yeah. So now we want to determine the range for A. Yeah. All right, using the simple basic inequalities. Yeah. N equals A times B, then because B greater or equal to A, if we replace B by A, so the product of A and B should be greater or equal to A squared. Yeah. Yeah. Greater or equal to. Yeah, that's the basic property, algebraic property of inequalities. Yeah. All right. That means n greater or equal to n squared. Yeah. But we know A is greater or equal to 2. The upper bound of A, we take square root. But we know A is an integer. So when we take square root, we can apply the floor function of the square root of n. Yeah. Because square root of n may not be an integer. If it's not an integer, we can take the floor function of root of m. Yeah. So we get an integer expression. So this is the range for A. Yeah. Because n is given. N is given. So between 2 and the root of n floor function. That's the range for the smaller factor of n. Yeah. All right. So this is the property. Yeah. So the new property. Okay. Yeah. At the beginning, we didn't know. So now we discover it. Yeah. Then we can use this property to explain why we can stop right after 7. Okay? Yeah. Yeah. All right. So here, let us look at the range for A. The range for A, because n equals 100, right? Yeah. The largest number in our table, that's 100. Root of 100, that's 10, right? 10 integer, so the floor function also 10. Yeah. So between 2 and 10, but we want to look at the prime numbers in this range, right? Yeah. Because when we consider that A factor, yeah, when we do the testing, we want to use the prime numbers. And the prime numbers, the 7 is the largest prime number in the range. All right, so here, let me look at the question. Oh, yeah, okay. All right, yeah. Yeah, let me check the, chat area. Yeah, so no question. Yeah. All right. Yeah. So that's why after we work on multiple of 7s, then it's enough. Yeah. Because the next one, 11, when you look at the next prime numbers in the table, 11 already out of this range, right? Outside this range. So we don't need to look at any number outside this range. That means we can stop. Okay? Yeah. So using this property, we can reduce the number of tests. Yeah. So when we work on the sieve, we can stop much earlier. Yeah. Otherwise, if you want to, do the remaining many rounds of sieves, you are wasting your time. Yeah. Okay, not efficient. Yeah. Yeah. So this is the sieve of Eratosthenes algorithm. Okay? Yeah. So we complete this algorithm. Yeah. Yeah. But this is still part of our understanding because our goal, we want to solve problem number 2. That's our goal. Okay? Yeah.
I have a question.
Yes?
So are we comparing the a times b to a squared because we're assuming like the case where a and b are equal to each other? So at that point you're just doing like b equals a, and so that's why we're getting the a squared? Like where's the a squared coming from?
Oh, good. Yeah. All right. Let me explain. So look at this requirement. Yeah. In this requirement, we assume a less than or equal to b, right? Yeah. Look at here. Yeah. Then, when we estimate this product, can we replace b by a? Replace b by a. But when you replace b by a, you make the second factor smaller, right? You make the second factor smaller, then the product should be smaller, right? So that's why we use this greater or equal sign. Yeah.
Okay.
Yeah.
So you use the smaller factor because we're trying to minimize the number of rounds.
Right. Yeah. Yeah. So here, yeah, minimum, right. Yeah. Yeah, because we want to determine the range for A. And here, minimum round, so here, the upper bound of A. Upper bound of A. Yeah. So when we hit the upper bound, we should stop. That means after the upper bound, you do not need to do anything. So that's the meaning, minimize, right? Yeah, minimize the rounds of sieves. Sieve. Yeah. Right. Rounds of sieves. Yeah. Good. Yeah. All right. Yeah. Yeah, I can hear, so it's good. So you can ask me, yeah, because sometimes when you ask me questions, if I do not respond, yeah, probably I couldn't hear, so you can type messages, yeah. But now, yeah, it's good. I can hear. Yeah. All right. So now I move to the next topic. Yeah. All right. Yeah. So only use prime in this range. Yeah. Yeah. That means when we write our program, we use this range. Okay. Because later we need to write a program. Yeah. So you know why. What's the reason we use this range? Yeah. All right. Yeah, 2nd century, yeah, not 3rd century, okay? Yeah, so the earliest reference of this algorithm, yeah, 2nd century. Yeah. All right, next, implementation. Yeah, so here, summary, as a summary. So let me go through the implementation. Yeah, all right. Begin with the first number P in the table. Yeah. Here, the first time 2. First number in the table. Then we remove from the list all the non-trivial multiples of p's. Yeah, that's p's. All right. Declare p to be prime. Yeah. Yeah. All right. And cross off all the multiples of that number in the table. Yeah, so here we are, not a p, okay? Yeah, keep that p. Yeah, so all the other multiples. Yeah, because some students may argue p itself is also multiple of p, right? Yeah, so that's why I said non-trivial multiples. Yeah, all right. Oh, starting from p squared. Yeah, in this way, then you don't have that confusion. Yeah, because the starting point you can jump. Yeah. So here, yp squared. I want to explain yp squared. Remember a squared, right? Yeah. So let's recall n equals a times b greater or equal to a squared, right? Yeah. So this time a equals p. Okay. Then a squared equals p squared. Okay. That means the smallest composite number is p squared. So the first composite number you should cross off is p squared. Okay? Yeah. If the number less than p squared, don't look at it. Okay? Yeah, because you will not find such composite number there. Yeah. So p squared. But after p squared, then next p multiple, another next p multiple, and so on. Okay? All right. Then, after you finish the current sieve round, then go the next sieve round, find next number in the table after p. Yeah, you set it as a new p. Yeah, so here 3. Okay, next one. So that is not yet crossed off. Yeah. So you set your new p. That's your new p. Yeah. To then repeat from step 1. Yeah. Keep doing. Yeah. Sieve like this. Yeah. All right. Until until p in the range, right? Yeah. Because we specify the range. Yeah. When you select the p, you do it in this range. Okay? Yeah. After you finish, finish processing the numbers in this range, you stop. Okay? All right. Then another thing. Yeah. So because here the last thing about this algorithm. Yeah. When you do the implementation, when you need to write a code, yeah. When people need to write a code, implement this algorithm. Yeah. So there is one subtle problem you need to think about. So what's that? The subtle problem. So that is because here in this one, every time we want to select a p, that means we want to select integer. We want to select we want to select prime. For example, 4 we do not want to select. 4, all right? Skip 4, okay? 6 we want to skip, okay? So, but we work on 5 and so on. Yeah. But the question is, so here there is a technical question. If you do that, if you want to skip those composite numbers in this range, when you write the code, it's relatively hard. How do you skip? Right? So you have that question. Now, when you write your code, that part is, not very easy to skip those numbers. Yeah. So for that reason, because if you want to make your code easier to write, then people just don't skip. Go through all the numbers one by one in this range. Okay? Because when you work on 4 multiples of 4, basically you do nothing. Yeah. So you do useless work. Yeah. But the code is easier to write. Okay? The code is easier to write. Yeah. Although you do some necessary work, but the code is easier to write. So for that reason, we take the easier coding way. Yeah. So in this situation, we take the easier coding way. Yeah. So here, this comment, yeah, because this comment, if you read a Wikipedia page, yeah, because when I talk, so here, I took the material, sieve of Aristosthenes material from the Wikipedia. Yeah. So in the Wikipedia, you can see at the end of this algorithm, so that is the comment. There is a comment, yeah, telling you, yeah, easier way to, cross off all the multiples. Yeah, you're just working on this range. Yeah. Now the primes in this range. Yeah, ideally, you want to work on the primes in this range, right? Yeah, but to find the numbers of prime in this range, pretty hard. Yeah, from the coding perspective, pretty hard. Yeah, so that's why people want to make their coding easier. So just doing everything in this range. Yeah, that's the comment. Yeah. All right, so we complete this algorithm. Yeah. Now the last one, trial division. Yeah. To solve our problem number 2, the trial division. Yeah. And then later when you do project 2, so here, yeah, this part, preparing for our programming project number 2. When you work on the project number, you need to write a code of this one, but not the previous one. Not the sieve of Aristosthenes algorithm. Yeah. Not that one. Okay? That one, you don't need to write that algorithm, previous one. But you need to write code of this algorithm. Okay? All right. So let's look at the solution. This time we need to get a solution of problem number 2. Okay. All right. Idea. Modify the algorithm of the sieve of Eratosthenes algorithm. Okay, all right. Recall, if n is a composite number, then the smallest prime factor p of n is in this range. Yeah, all right. Next, implement the following steps. Yeah, remember? So here, implement this. We call the trial division. Trial division. Yeah. So here, yeah, let me go back to original question. Given a positive integer n, how to represent it in a product of prime numbers? Now, we need to do, so this time, we cannot use that sieve of Aristosthenes algorithm. We cannot use this one, right? So here, so we have to find the prime factor. We have to find the prime factor directly. We have to find the prime factor directly. Okay? Yeah. Sorry, we have to. Yeah, actually. Yeah, so here, yeah, product of prime numbers. Yeah, so each factor should be a prime. Each factor should be a prime. Prime in this range. Okay? Yeah. But we just go through the numbers in this list, one after another. One after another. Okay? All right. Yeah. All right. So then, trial division. We need to do testing. Trial. Testing. Yeah. All right. Yeah. The first step, select the smallest number p in the list that has not been tested. The first one we test the first number in the list, 2. Yeah. Second one, 3, and so on. Yeah. Has not been tested. Okay, all right. So we select smallest number p in the list. Yeah. Yeah. Then we apply this modular operation. M mod p. We know we do integer division, but we only look at its remainder, right? Yeah. So this percent sign, we know that's the modular operation. Modular operation. Mod. Okay? Yeah. We use mod operator. Okay? Yeah. So then, if the remainder is 0, remainder 0, that means n is a multiple of p. N is a multiple of p, then there is a p factor, so we should extract that p factor out of n and take a division to remove the p factor, then work on the quotient. After you take out p factor, then you still have the quotient for further processing, right? Quotient for further processing. Yeah. All right. So if it is true, add p to the factor list. Yeah. Because the result, the output. So here you consider the factor list. That's our output. Output. You should get a list of prime factors, right? Prime factors. So we add p to the output list. That output list is the prime factor list. Okay? And set n equals n over p, the quotient. Yeah. Because after you take out the one p factor, the remaining numbers, factors, the remaining factors of n, they are in the quotient of this division. N over p division. Okay? Yep. So you update n. Then repeat that process. Yeah. You repeat. You need to, so after you have this new n, you need to model the same p another time. Yeah. Because this n may have factor of p to some exponent number, right? Yeah. Not because you want to see what is the largest power of p that is a factor of n, right? You want to see that. Largest possible power of p that is a factor of n. So that's why you repeat this process until when you do the modular operation, you do not get 0. So you get out. You get out of this while loop. So this should be a while loop. Okay? Out of this while loop. Okay? Yeah. Then, after you get out of this while loop, you should move to the next p in the list, right? You finish. Yeah. So you finish this, for example, 2. Then you go to your next p, 3 in the list. Okay? All right. Yeah. After we finish the testing, the whole list, okay? Yeah. Output the factor list in certain format. Certain format. So you have a factor list. Yeah. But remember that p could be repeated multiple times, right? Yeah. Because your p probably repeated, 3 times. Then your next prime, let me call it q. Q probably repeated, twice, and so on. Okay? So you have many prime numbers. So each prime number repeated a certain number of times. Yeah. So then you should output that factor list. Yeah. Representing your prime factors in certain format. So here, this certain format, I delay it. I delay to the next slide, I describe that format. All right. Yeah. the unique factorization theorem. So this time, in number theory, there is a very important theorem called unique factorization theorem. Uniqueness. So if we write the prime factorization in some standard way, because you may have many different ways to write prime factorization, but this time we want to define some standard way. If you use the standard way, then the prime factorization must, for a given number, must be unique. So that's a nice property. So what's that standard way? All right, so the theorem of this important theorem in number theory, any positive integer can be written as a product of primes in one and only one way. So what's that way? Standard way. So that standard way we call prime power decomposition. So we have a name for it. That standard decomposition way called prime power decomposition. What's that? So the format is each positive integer can be written in exactly one way in the following form, this form. N equals P1, the first, so first prime factor, P1 to the E1, certain exponent number, E1. Okay, then P2, the second prime factor, to the E2 exponent number, and so on. And the last one, Pk to the Ek. And we know these P numbers, P1, P2, in ascending order. If we need to write it in ascending order. Okay? All right. Actually, so the standard form, so we write in ascending order. Although here in this form, we only require Pi different from Pj. So not necessary in ascending order, right? Not necessary. In this theorem, it's not necessary in ascending order. But we treat as the same form. But in our program, so we want to write these P numbers in ascending order. Okay? So then it's, more convenient. More convenient. If write it in ascending order. Otherwise, if you do not require ascending order, then different people may use different order of P's, right? So then, when you compare two prime power decomposition form, then much harder, because the order messy, right? The order could be very messy. So that's why, in order to make our comparison easier, so we want to write them in ascending order for convenience. All right. So implementation here, the pseudocode. So here, the last thing I want to talk about is I want to explain the pseudocode. So this pseudocode, I take the screenshot from the Wikipedia page. So here I want to explain a little bit. Later you need to write a program, implement this algorithm. Child division algorithm. Input integer n to be factored. Okay? Positive integer n to be factored. Output list capital F of prime factors of n. Okay? So later, in my project description, I need to describe the format of this list. Because when you write a list, so you want to keep some format. Okay? All right. Then, P, when you start, so you take the data range. So P, remember your little p, all your little p's come from a list, right? So that is set of primes, set of all primes. Although here set of all primes, because remember the comment I made at the end of the last topic, yeah, because to get a list all the primes, that's hard, right? That's, you know, from the coding point of view, hard, okay? From coding point of view, it's hard. So there, we just, you know, we just do this, you know, the whole list. Okay, the comment. That comment we can also use here. Okay, so this p list, we, you know, for a convenient way, we can use that one. Yeah. Ideally, we should get a set of all primes in as the list. Ideally, but coding relatively hard, so people take the, you know, easier way for the coding. Okay, all right. Yeah, initial output list. This is the output list, empty list of factors. Then, for each loop, you need to go through all the little p's in this list. Okay, all the little p's. So, for the current p, that inside inner loop, this while loop. You need to work on this while loop. Okay, yeah. So for 1p, you need to apply this mod operation. Keep applying this mod operation. If it's 0, if the remainder is 0, you should do again. Yeah, another time, until the remainder is not 0, you get out of the while loop. If it's 0, that means you added this p to the list of f. Then replace current n by the quotient n over p. Then another iteration in the while loop until you extract all the possible p factors from n. Okay? Then you move to the next p in the capital P list. Okay? That's the meaning. That's, you know, for loop. Outer for loop, inner while loop. All right. After that, if then the last two lines produce the output. If capital F is empty, yeah, that means your current n number is a prime. Original n number is a prime. So you get a prime. Okay? So when you get a prime, you do not need to do factorization. Only one number. So you do not do factorization. Okay? Yeah. So add a factor n to f. Yeah, because then your f only you have one number in your output list. If you have only one number in your f list, then that means this n is a prime. Okay? Yeah. So that's the meaning of this trial division algorithm. Okay? Yeah? Yeah. So in your project number 2, you need to implement this child division algorithm. Okay? Yeah. So not immediately, yeah, but sooner or later. If you want to try, yeah, so you can do it. Okay? So you can write the code of this algorithm and do experiments. Yeah. Then later, when we work on project number 2, then you already have this function. Okay? Yeah. All right. Any question? So we finish part A. Okay. Yeah. So we have a few minutes before the break time. Yeah. So let me move to part B. So let me talk about the problem first. Yeah. Another problem first. Yeah. All right. So here, let me get out of the part A. Yeah. And jump to part B. All right. efficient polynomial evaluation. B.1, evaluate the polynomial. Oh, I need to change my pen color. Every time when I get out, I need to change my pen color. All right, yeah. Evaluate the polynomial. First, our computing problem number 3. Evaluate a polynomial. It's a simple problem. Yeah? Polynomial. So everyone knows. Everyone is familiar with the polynomial. Yeah. All right. The question. Our data is a polynomial. Yeah. So the standard form of a polynomial we write in this way. Okay. Yeah. With coefficients a, 0, 1. Yeah. So these coefficients we store in an array, input array. We store all the coefficients of a polynomial. Yeah. Then x is the variable. So we can take different values for x variable. Then we need to evaluate this capital P polynomial. Yeah. All right. Question. How to evaluate this P polynomial efficiently? So here, the important thing is efficiently. Okay? Yeah, that's important. Yeah. Because everyone knows how to evaluate this polynomial. Yeah. So if I ask you to write a program to find the value of this polynomial, it's very easy, right? So you use a for loop, yeah, multiplication, addition, so you can find the correct value of this polynomial easily. Yeah. But the question is, your algorithm may not be very efficient. Okay? Yeah. So we want to find an efficient algorithm. Okay? Yeah? All right. Then, understanding. Yeah. So here I give you the reference. The reference section 6.1, the later chapters. Yeah. So another reason why I jumped to this chapter, because I need to give you programming project number 1. So this topic is our programming project number 1. Okay? Yeah. And the knowledge you need, you have the knowledge. Yeah, polynomial knowledge. Yeah. Multiplication, addition. So everyone knows how to do multiplication additions. Yeah. So you have the knowledge needed for this topic. Yeah. So we need to, in order to have more programming time, yeah, so that's why we need to start our project topic as early as possible. Yeah. All right. First try. The first try, brute force method, right? Yeah. So I mentioned last time. Yeah. When we have no idea, when we do not have some better idea, the first idea we can start the brute force method. Okay? Yeah. Just some relatively simple way we can solve the problem. Yeah. All right. So we just use the straightforward algorithm. All right, so let's look at this general representation. Yeah. You have multiple terms. Yeah. When you calculate the value of this polynomial, you need to evaluate individual terms, right? Yeah. Individual terms. After that, you add up all the terms. Yeah. So that's the, straightforward way, the obvious way. Yeah. Now we work on each term. And when we work, we want to look at how many multiplications we need. Yeah. Here we need to count number of additions and number of multiplications. So we separate. We have 2 different operations we need to use. Yeah. Yeah. Additions, multiplications. Yeah. All right. Here, because for each this is a typical term. Yeah. Individual. So each typical term, we only have multiplications. Yeah, we don't have addition here. So we only have multiplication here. Now the question, how many multiplications do you need to calculate this single term? Yeah. Just one, this typical term. Yeah. Suppose the k number is given. Okay? If you know the k number, then you need to calculate the a sub k coefficient times the monomial x to the kth power monomial. To calculate this term, how many multiplications do you need? Think about that. Think about that. A simple question, but you need to make sure your counting is correct. Here, we need to do the counting. We count the number of multiplications. Make sure your counting is correct. Yeah. All right. So here, the problem. Still, we need to go to the problem solving. Yeah. Here, we need to consider the strategy to solve this problem, the problem solving strategy. Yeah. So the strategy here, what's the strategy? Yeah. Here, do some experiments. So that's strategy. Yeah. You do some experiments for small k numbers. Yeah. All right. When k equals 1, yeah, you calculate the term a1 times x. How many multiplications do you need? a1 times x. Yeah. One multiplication, right? Yeah. All right. Next, another experiment. When k equals 2, so your current term becomes a2 times x squared. How many multiplications? Okay? Yeah. X squared, you need to one multiplication, right? X times x squared, 1. Then a2 coefficient times x squared, your second multiplication. So you need 2 multiplications, all right? Then let's do another experiment. a3 times x cubed, how many multiplications do you need? Okay? a3 times x cubed, you need 2 multiplication, right? X times x times x, 2 multiplications. Then another multiplication, a3 times x cubed. So you need 3. Is it enough to find the rule? Can you see the rule? Yeah. Because after you do some simple experiments, you can easily find the rule, right? Yeah. So now you apply that rule on this general case. ak times x to the k. So what is the answer? How many multiplications do you need for the general term? Okay? Yeah. Type your answer in the chat area. Yeah. Type your answer. Yeah. So I just want to see one student. Good. Yeah. Yeah. K. Yeah. Answer is K. Here we apply the induction. Right? K equals 1. Answer is 1. K equals 2. Answer is 2. K equals 3. Answer is 3. K equals K. Answer is K. Yeah. That's the induction. Yeah. All right. Yeah. Yeah. Now it's the break time. So let me stop right here. Then you take a break. Then come back at 7 o'clock.